So, welcome back to lectures on engineering mathematics 2. This is lecture number 59 on applications of Laplace transforms for solving differential equations. So, in this lecture we will be discussing the initial value problems and the Laplace transform technique for solving such initial value problems, and also we will go through some integral equations. So, in general when we are talking about the solution of integral or differential equations, these are the key steps we need to follow. The first is we need to take the Laplace transform on both the sides of the given differential or integral equation. The second step, so we will simplify this to get something like Laplace of y is equal to some function of s from this transformed equation. So, we have the given equation. After taking the Laplace transform, we have the transformed equation, and that we will simplify to have this form L y is equal to f s. And then finally, we will apply the inverse transform to get the solution y is equal to L inverse f s. So, these three are the key steps for solving any differential equation using this Laplace transform. Just a note, in this process we will assume that the solution of the given differential equation is continuous and is of exponential order, so that the Laplace transform exists. Indeed, we need piecewise continuity, but in differential equations we most of the time we have a solution which is even continuous and of course of piecewise of exponential order. So, that all the Laplace transform, when we are talking about taking the Laplace transform both the sides of a given differential equation. So, naturally we have to assume that the Laplace transform exists. So, the process will be clear with the following example, and then we will be doing many other examples. So, here we need to solve the differential equation or the initial value problem, this d 2 y over d t square plus y is equal to 1. Initial values means we have these conditions are given at a single point t equal to 0. So, this t equal to 0, two conditions are given, it is a second order differential equation. So, we need two conditions to solve to get a unique solution of this given differential equation. So, we will apply the Laplace transform. So, Laplace transform on this double derivative plus Laplace transform on this y, and due to linearity we can apply to each, and the right hand side it is a Laplace transform of 1. So, this is the first step. In each problem we will use it. The second one, now we have to use this Laplace of y double prime, that means the derivative theorem, to remove these derivatives. So, we have this derivative theorem that s square L y minus s y 0 minus y 0, that is exactly the Laplace transform of this L y double prime. Then we have L y, and the right hand side we have L 1. So, at this step itself we can use these initial conditions, y 0 is given as 0 and y prime is also given as 0. So, we can use these given initial conditions. So, these conditions are incorporated just after applying the Laplace transform, taking the Laplace transform on both the sides of the equation. So, here this is 0 and this is 0. So, we have s square and then plus 1 when we take this L y common. So, this is L y s 1 plus s square, and the right hand side this Laplace of 1 is 1 over s. So, now we can divide this by 1 plus s square. So, we get L y is equal to 1 over s 1 plus s square, and then the final step is to take the inverse here. The third step is to take the inverse, so that we get y from here. So, taking the inverse of this, we can either apply the convolution theorem on this, or we can do the partial fractions. This we have already discussed before. So, we will not spend time on taking this inverse Laplace transform. So, for instance, we can do this partial fractions 1 over s minus s over 1 plus s square. So, this is the Laplace transform of y, and then we can apply this inverse technique. So, y t will be L inverse 1 over s minus this L inverse s over 1 plus s square. So, L inverse 1 over s we know it is 1, and the L inverse s over s square plus 1, that is cos t. So, we have the solution y t as 1 minus cos t. Here we have another problem, x double derivative with respect to t, x t and cos 2 t. Here these are the initial conditions given. So, again the process will remain the same. We will take the Laplace transform, simplify it, incorporating these initial conditions, and finally, we will go for the inverse inverse Laplace transform. So, taking this Laplace transform on this x double prime plus x t and the right hand side on cos 2 t, we will apply again this derivative theorem, s square x s minus s x 0 minus s prime, that is the Laplace transform of this double derivative, plus the Laplace transform of x t, and the right hand side Laplace transform of cos 2 t. So, now we can substitute this x 0, which is 0 there, x prime is 1. So, we have one term there. So, then we can simplify for this x s, which is given here now, and again the same process. So, we can do partial fractions at this stage, and then we have to take the inverse finally, which is from here it is a cos t, the inverse of this will be again cos 2 t, and here it will be sin t. So, this is the solution of the given differential equation, which also incorporates these initial conditions, because they are used in the process. So, the advantage of this Laplace transform is that directly in after taking the Laplace transform, we can use the given initial conditions, and finally, we will get just the solution of the given problem. So, here we have y double prime plus y is equal to c times some constant times the Heaviside function h t minus a. So, it takes the value 1 when t is greater than equal to a, otherwise 0, and then we have initial conditions, and this is indeed a very good application of the Laplace transform, because this is a discontinuous function sitting at the right hand side. Dealing with this directly by some other means would be difficult, but here since we know the Laplace transform of the Heaviside function, it can easily be handled. So, taking the Laplace transform, we use this derivative theorem here, and then we have y s, the right hand side we have c, and then we have this Laplace of this t minus a, Heaviside function t minus a, which is given here. We can just integrate a to 1, the function is 1 e power minus s t d t. So, which is just e power minus a s over s. So, here we have s square plus 1 y e is equal to 1 plus c e power minus a s over s, and we have used this initial condition y prime 0 as 1. So, simplifying this for y s. So, we have these expressions now for y s, including the c there, and then we can go for the inverse. So, after taking the inverse here, it is clear it will be sin t, and now here we have e power minus a s, and then we have s square plus 1. So, we have to first go for this partial fractions. For instance, it is 1 over s and s is over s square plus 1, and then e power minus a s. So, we have to deal now how to get the inverse. Remember the shifting theorem, where we have the L inverse of this e power minus a s and f s will be just f t minus a, f t minus a, and h t minus a. This is the inverse here. So, e power minus a s is sitting there too, and we have f s. So, f s is 1 over s and then s over s square minus 1. There are two functions. The inverse of this is 1, and the inverse of s is s over s square plus 1 is cos t. So, then there will be a shift in cos t, that t will be replaced by t minus a, and there will be a factor h t minus a, and then we need to that is all. So, this we can handle easily now. So, we have the Heaviside function t minus a, and this is the 1 minus cos t inverse of this, but because of this shifting theorem there will be shift here also. So, we have constant times the Heaviside function t minus a and 1 minus cos t minus a. Solve the following problem. We have the double derivative plus this x, right hand side there are two Heaviside functions, but they can be handled similarly as in the previous problem. So, after taking the Laplace transform, we have s square x s plus this x s coming from here, because these two are 0, x 0 and x prime. So, there will be no other term other than this s 0 x s once we apply here the derivative theorem. Here the Laplace of this Heaviside t minus 1 is e power minus a I minus s over s, and in this case it is e power minus 5 s over s, and then this x s will be e power minus a s over s s square plus 1 e power minus 5 s and again s into s square plus 1. So, again we have to realize that the L inverse over 1 over s square plus 1 is 1 minus cos t, and because of this e power minus 5 s we will have the shifting theorem which was used in previous example as well. So, we have 1 minus cos t minus 1, this is the shift t minus 1 because of this first e power minus s. In the second case we have shift by this 5. So, t minus 5, and again same thing 1 minus cos t minus 5, the Heaviside function t minus 5. Solve the initial value problem. So, we have here again with the delta term delta t minus 3 and h t minus 3. So, here also we can use this while taking the Laplace transform there, we can use the shifting theorem f t minus a h t minus a is equal to e power minus a s f s. So, the right hand side here after taking the Laplace transform we will have e power minus 3 s and the Laplace transform of this delta t which is 1. So, here the right hand side will be having only e power minus 3 s once we take the Laplace transform. Here we have for the double prime these three terms using this derivative theorem, then we have 2 times again the derivative theorem there, and then 2 times the y s. So, here now we can combine. So, with y s we have s square 2 s plus 1, the right hand side we have e power minus 3 s, and we have used these initial conditions. Then we have y s in terms of completely the function of s. So, 1 over s plus 1 whole square plus 1 and e power minus this 3 s. So, the y t when we take the inverse there. So, we have to now get this inverse, and again this shifting theorem will help for the inverse. So, whenever e power minus a s is sitting and we are taking the L inverse, this will be f t minus a. So, there will be a shift in the function. So, here also we have the shift by t minus t will be replaced by t minus 3, but we need to get first the Laplace inverse of this 1 over s plus 1 is square plus 1. So, it is of kind 1 over s square plus 1, and that first shifting theorem we have to apply there to, because e power a t f t is f s minus a. So, that we can apply here to remove this shift there. So, it will be e power minus t and then this is sin t. So, there will be e power minus t sin t, and because of this e power minus 3 s there will be a shift in t by t minus 3, because the Laplace inverse of this 1 over s plus 1 is square plus 1 will be e power minus t and sin t, and then because of this e power minus 3 s, this t will be replaced by t minus 3, this will be also replaced by t minus 3, and there will be a factor of this Heaviside function t minus 3. Okay, so, now we will find the general solution in this case, meaning that no initial conditions are given, but we can still deal with this Laplace transform. So, we will just keep those unknowns as it is and then proceed with the same process. So, here we take the Laplace transform. So, this is the derivative theorem for y double prime, then we have y s, and then the right hand side will give us 1 over s plus 1, that is the Laplace transform of e power minus t. So, here this y 0 and y prime 0 are not given. So, we will just take them as some constant. So, let us take this y 0 and y 1, and then we have s square plus 1 y s is equal to this. So, we will again bring into this form that y s is equal to this function of s, and then here we can do this partial fractions. That means, we have 1 over s plus 1 s minus 1 over s square plus 1, and this with y naught s over s square, with y 1 we have 1 over s square plus 1. And then, so taking the Laplace inverse, we will get 1 by 2 e power minus t. Here also we will get 1 by 2 with minus sign, and s over s square plus 1 will give cos t. Then we have again here the plus half, then we have sin t, we have y naught cos t, and we have y 1 sin t again. So, finally, we have y t is equal to half e power minus t, and then this cos t will give y naught minus half, and with sin t y 1 plus half, which can be treated as a different another constant here, the c naught and the c 1. So, our general solution of the given differential equation is half e power minus t, some constant c naught cos t, some another constant general constant c 1 sin t. So, given the conditions, we can compute at the end also once we have the general solution, but in general when we apply the Laplace transform, the conditions are given, we can fit them in after just first step, and then calculations will be much easier. So, here we have for instance this fourth order differential equation with right hand side having delta x minus 1, the initial conditions are given all these zeros. So, we can apply again the Laplace transform, and all these will become 0 because of this initial conditions. Sorry, they are not initial conditions, these are this is the boundary value problem actually. So, boundary value problem, because at 2 points these conditions are given, one is at 0 and the other two conditions are given at 2. So, this is not the initial value problem, it is boundary value problem. Boundary value problem where the conditions are given at 2 different points. So, the 2 conditions are given at 0, other 2 are given at 2. So, here these conditions can be incorporated directly at this point after taking the Laplace transform, but these 2 conditions we cannot apply at this moment. First we will get the solution, general solution in that sense. So, we have now the derivative theorem S 4, and then we have y 0, y prime, y double prime, and then also the third derivative will appear in the derivative theorem. The right hand side we have the Dirac delta, this x minus 1, and its transform will be e power minus s, and there was a minus sign which remain as it is here. So, after simplifying, because we have to now consider for instance this y naught is 0 and y double prime is 0. So, this term will vanish and also this term will vanish, but this will remain. So, we can take it as like C 1, and this coefficient we can take as C 2. So, we get this expression for y s, and then we know this shifting theorem which can be applied here for e power minus s, and there is a s 4 term here also the same thing, but there is no shifting theorem, no e power minus s. So, finally, we have due to this e power minus s there will be shift in 1. So, we have x minus 1 cube by 6 and the Heaviside function. So, sometimes we are using the notation u for the Heaviside function, somewhere we have used like h. So, here we have the C 1 x because of this, and then again the same thing, but without the shift here. So, we have x cube by 6, here also it was x cube by 6, but because of this e power minus s there was a shift and multiplication by the Heaviside function. And now, we can apply these two conditions which were not used so far. So, y 2 is 0. So, we will just pass here x is equal to 2 and simplify this. So, we will get one equation C 1 C 2, and the other equation we have to take the double derivative of the given solution. So, after taking from here the double derivative, we will set to 2 x is equal to 2 and we will get another equation which is just in C 2. So, from the second equation we will get straight away C 2 is equal to half for instance, and that C 2 can be plugged in this first equation and we can get C 1 straightforward. So, having C 1 and C 2 we can just substitute in that solution and we will get the solution of the given differential equation. So, here we have the initial value problem because these conditions are given at 0 only, and here the difference is that this is t y prime. So, we have the variable coefficients, but we can deal again with the Laplace transform. So, we have s square, the derivative theorem for y prime goes up to this, and there is a t times. So, we have already gone through the properties of Laplace transform. So, Laplace of this t y prime is minus d over ds Laplace of y prime and minus 2 y, and then we have 4 times this Laplace of 1 right hand side. So, here we have s square y s, and we have used this condition y 0 as 1. So, there will be a term s here, and then minus this d over ds and the Laplace of y. So, again we have to y prime. So, we have to use the derivative theorem minus this 2 y s, the right hand side we have 4 over this s, the Laplace of 1 is 1 over s, and here now we can use these initial conditions. So, indeed does not matter here because d over ds. So, that will make this 0. So, we have this d over ds of s y. So, we can use the product rule. Finally, we will get this differential equation in this case, not just the algebraic equation, because of this t there and this derivative term has appeared. So, we will get a differential equation when we have these coefficients depending on the independent variable. So, we have dy over ds plus this 3 over s minus s and y s right hand side minus 4 over s square plus 1, and that this is a linear equation. So, we have to find the integrating factor and then we can write down its solution. So, the rest is just simplification and to get again this y s. So, you can go forward. So, after again here integration by parts, because there will be the terms. So, the first integral will be like minus 4 s e power minus s square by 2, and then there will be integral with this s cube and e power minus s square by 2 ds. So, that is the integral sitting here right hand side. The first readily will give here because the derivative of this is sitting here with minus sign indeed. So, minus s. So, we will have 4 e power minus s square by 2, that is the integration. Here we have to apply the chain rule again. So, the chain rule says that this can be written as s square and then s we can bring this with e power minus s square by 2. So, this term can be integrated and this can be differentiated. So, here with the minus sign, because we need to integrate this and there is a minus sign there. So, minus s square e power minus s square, the derivative of s square will be 2 s, and again the derivative e power minus s square by 2 with this minus sign. So, it has become plus and then we have c. So, here we can integrate again this and this is again minus e power minus s square by 2 with the 2, here it was with 4. So, the 4 will remain and then the 4 and then minus 2. So, this will be like 2 e power minus s square by 2 and then we can divide by this. So, finally, we get the expression for this y s in terms of s, and since we assumed already that y t be piecewise continued exponential order, and we know the property of the Laplace transform, that its transform must go to 0 as s goes to infinity. So, if this property needs to be fulfilled here, then this c has to be 0, because if c is non-zero because of this e power s square by 2, this will go to infinity. So, to have this property of the Laplace transform, that y s, the Laplace transform of of this function must go to 0 as s goes to infinity. In that case, we got that this c has to be 0, otherwise this is not possible. So, then this term will vanish and then we can take the inverse. So, this 2 over s cube will give t square and 1 over s will give 1. So, we have t square minus 1 the function this y t. Solve the initial value problem. So, here again we have the variable coefficient. So, t y double prime plus y prime plus t y equal to 0 and these initial conditions are given. So, we will follow the same step, we will take the Laplace transform and because of t there will be a term d over ds. So, after this simplifying, because here we have to there are two places where d over ds will appear and then the derivative theorem will be applicable here. Then you have this L y prime, again the derivative theorem, and then we have minus d over ds there. So, after simplifying what we observe, because we have incorporated these initial conditions also here. So, we will get this differential equation, a simple differential equation, and then whose solution can be written simply by this y s c over square root 1 plus s square. And just to recall that if we take the inverse here, this is the inverse of this special function which we have discussed before j 0 t. So, there was this was discussed in the earlier lecture, and also we recall from there that j 0 t was actually 1 and then here y 0 is given as 1. So, we can compute this c also. So, with these two conditions which that function follows and also y 0 1 is given here in the problem, we find that c is equal to 1. So, we have y t is equal to j 0 t. Now, coming to the integral equations. So, we have f t is equal to g t of this nature, or we can have the differential equation of this nature, that g t is equal to k t u f u d u, and the question is what is f? F is unknown basically in this problem, and how to get this f? We will again use this Laplace transform. So, suppose and under this condition this Laplace transform is very much useful. So, if k t u is of this kind, k a function of t minus u here. So, this is k t minus u, here also we have this k t minus u. So, in that case we can easily apply the Laplace transform, and so we have here f s, we have for instance from the first equation g s, and here we have the convolution theorem, because this became now convolution integral if we have instead of this k t u k t minus u and f u. So, we will get k s and f s. Once we are here, we can again find for this f s the expression for f s, and finally, the inverse transform will allow the solution. So, it is a simple steps again, but the similar one. So, let us go through some of the examples. So, for instance, we have f t is equal to e power minus t, and then this integral which is the convolution integral. There is a function f and there is a function sine. So, after taking the Laplace transform, we have here the Laplace transform of e power minus t and then the convolution theorem. So, this will be the product of the Laplace of sine t and with the product Laplace of f t. So, taking now common Laplace of f t, we get Laplace f t is equal to this, which again can be inverted for the Laplace transform, and having these partial fractions, now we can take the inverse. So, it is 2 e power minus t from here, then t from here, and the 1 from the last term. So, we have 2 e power minus t plus t and then minus 1 is the f t. Here we have the x t is equal to e power minus t and sine hyperbolic function t minus tau x tau d tau. So, again we have a similar situation that this is a product of these two functions. So, the convolution product, and then we can apply the convolution theorem. So, that will be the product of the Laplace transform. So, having that, we have the x s here, and then for e power minus t we have 1 over s plus 1, and in this case this will be the product. So, the Laplace of sine hyperbolic will be 1 over s square minus 1, and the product of the Laplace of x tau, that is x s. So, we have x s is equal to this one, and that means this s minus 1 over s square minus 2, and we have s over s square minus 2 minus 1 over s square minus 1, and taking this Laplace inverse we will get cos hyperbolic square root 2 t sin hyperbolic square root t with this minus 1 over root 2, that will be just adjusted because s square minus this a square will be coming there. So, that is the just the after getting this inverse we get the Laplace we get the solution of the given differential equation. Here we have t square is equal to e power tau and x tau day tau. So, here again we will apply the same principle. So, 2 over s cube, that is the Laplace transform of t square. Then we have this integral there, and we have already learned that the Laplace transform of the integral only 1 over s factor will come there, and the Laplace transform of this integrand, that is e power t and x t. So, e power t x t the Laplace transform, because of the integral we have 1 over s term. So, this is nothing but 1 over s and x s minus 1. So, again the shifting theorem here, because the Laplace of e power t x t, that will be the Laplace transform of x t is x s, and there will be a shift because of this exponential function. So, we have x s minus 1. So, we have x s minus 1 as 2 over s square, or x s as 2 over s plus 1 whole square. So, s is replaced by s plus 1, and then if we invert this we have x t is equal to 2 e power minus t into t. So, that is all. These are the references we have used for preparing this lecture, and just to conclude, we have discussed the solution of integral and differential equations using Laplace transform. The key steps were we have to take the Laplace transform, and then we have to solve for Ly is equal to f s. In this case, if we have the constant coefficient equations, we directly get algebraic expression and we can easily get into this form, but we have the variable coefficient, then we need to solve some simple differential equations to again get this Ly is equal to f s form. The same steps we have for the integral equations. After applying the Laplace transform, we can directly get this Ly is equal to f s, and then final step would be taking the inverse from this, so that we can get the solution of the given differential equation. Well, so that is all for this lecture, and I thank you for your attention.